I'm delighted that the Nobel Committee has decided to recognize this particular discovery. There's no doubt that the discovery of the Higgs boson is a major event in particle physics. As you're probably aware, I was to some extent involved in this, in the theoretical developments in the beginning. In 1964, there were 3 papers published in Physical Review Letters within a few months. The first one by François Englert and Robert Brout from Brussels, the second by Peter Higgs from Edinburgh, and the third by 2 American colleagues, Gerald Guralnick and Carl Richard Hagen, and myself. I think all 3 papers reached essentially the same conclusions. They came from very different standpoints. In a sense, there's not that much overlap directly between the 3 papers, but we all reached essentially the same conclusions. Naturally enough, each of us believes that our own treatment was the clearest and most thorough. I welcome the award of the Nobel Prize, and I understand the difficulty that there would have been in recognizing our part of it directly, because the Nobel Committee is constrained by what is actually a self-imposed limitation to never award the prize to more than 3 people. And since there were 5 of us, there were 6 of us originally, but Robert Brout unfortunately died a year or 2 ago. And so there are 5 of us still remaining. And there is no doubt that our paper is the 3rd of the 3, so it's not in the least surprising that they recognized the first 2. We did our work independently, but we discovered the other 2 papers shortly before we published ours, so we did reference them. So that is my part in the story, and I did some more work later on the subject, but that's really a separate issue. So I think I should stop there and see if Jim wants to make any comments.
Perhaps I could say something about from the experimental point of view. I think this is wonderful news, as I think a great advance in science has been recognized both theoretically and experimentally in a sense. And Tom has given you the theoretical part and his own role in this a great intellectual leap, I would say, because it's not easy to understand that what has happened is that these guys have postulated there's a field that pervades the entire universe, and its quantum is the Higgs boson, which we have found. Now, what I would like to say is about the experiments. The search for the standard model Higgs boson was crucial in the design of both ATLAS and CMS experiments, and in fact, especially so in the region where we eventually found it, because it's very difficult to find it in this region. In a very harsh environment, there are order of 1 billion proton pairs which are interacting every second, and we had to dig out examples from 2,000 trillion interactions that we examined. The numbers of Higgs bosons are about 1,000, in fact. So, and I think to give you an idea of the experimental problems, let me just say something about a statement which was quite prevalent at the time. And it said that we think we know how to build a high-energy, high-luminosity hadron collider, but we don't have the technology to build detectors for it. So, in fact, as far as the detector challenge is concerned, enormous challenges had to be overcome in both the accelerator and the experiments. I know from CMS, for example, it was this high-field solenoid, the tracking systems, and the calorimeters. In the case of ATLAS, is also the superconducting toroid system, the calorimeters, and the tracking systems as well. Now, to bring you up to date, since the discovery that was announced in July last year, the amount of data that we've collected and analyzed was doubled. And this analysis now clearly indicates that the properties are very much like the properties you expect from the Standard Model Higgs boson, meaning that you looked at the spin and parity, its couplings to the other fundamental particles of the Standard Model, and they all, within the errors, confirm that it looks like a Standard Model Higgs boson. But there's another issue. So the first particle of the Standard Model was discovered about 115 years ago, which is the electron. And this is the last particle of the Standard Model. But we also know the Standard Model is incomplete. It describes quite well the visible universe, but not much of the rest of the universe, which is 95%. So we know it's incomplete. And also 20 years ago, when we were designing the experiment, we were looking at the Standard Model Higgs boson, we knew that if we found it, and the next question, because we found it in the region where the LHC was probing, that the next question would, why is it mass so low? Because there are some issues that arise with quantum corrections which float this mass up to very high energies, high masses rather. And so the fact that we found it means that there must be new physics. We don't know what that new physics is. So the LHC program is just starting. We've just only done 3 years. It's going to go on for about 2 decades more. And we all now hope that we'll get further clues and make further discoveries which will tell us further secrets of nature to be discovered. So there's a rich program to come as well. So I'll stop here perhaps.
Thank you, Jim. Over to questions from journalists. Stick your hand up if you can say where you're from as well. Nick.
It's Nick Collins from the Daily Telegraph. Just going back to the prize this morning, Professor Kibble, you explained quite clearly why we obviously the prize was awarded to 2 people, and it would have been difficult to give it to another. We couldn't have given it to another 3.
The youngest undergraduates who are just learning the field, and our esteemed colleagues who have driven it forward. I think we're all celebrating this moment.
Hannah Denton from the Times. Just to follow up on that, there has been quite a lot of discussion about whether this rule of only awarding the prize to 3 kind of in some ways arbitrary individuals to represent a discovery is sensible. And I realise it's difficult to criticise that without possibly sounding petulant about things, but do you think it's celebrating a kind of great human achievement? Do you think that there is something important?
I think the thing that excites, sort of inspired me in a sense is that here are these guys using mathematics and trying to understand how nature works, postulate something, which is, think about it. Somebody comes along and says there's a field which pervades the whole universe. Now that sounds a bit strange, in fact, and yet it's proof we have found. So I think the inspiration and the excitement you get from actually making a discovery is enormous, and I think that is the celebration. It was a great moment July last year when we announced it, and now it's all been, everything is pointing towards the Standard Model. But the other possibility of new physics is that there could be more than one Higgs boson, and in several theories this is possible. That's why we actually, experimentalists, still call it a Higgs boson. We do not call it the Higgs boson, because there's a possibility there are others around, and the one that we found would be subtly different from the Standard Model one if it's in conjunction with others.
Can I just follow up on that topic, maybe double time? So, Professor Kibble, you describe it as a self-imposed rule. Would you like to see that will change the number of people understanding?
Can I just ask Professor Kibble, I've spoken not to you but to some of your American colleagues previously about the time when you first published your work along with Higgs and the others, and they sort of described how at first it was not received particularly well, particularly by sort of more senior people in the profession who sort of told you, abandon what you're doing, it's complete rubbish, you'll never make a physicist. I just wondered if you could if you had any similar stories like that, if you could take us back to, it must be quite a nerve-wracking time.
I don't think I experienced that to the same extent. Partly because I was in this country and not in America. the culture of universities is slightly different in the two, and I think certainly my colleague and very good friend Jerry Guralnik did experience that, and he actually gave a number of talks about this and was very poorly received by some very eminent physicists, including Werner Heisenberg.
Yeah, I just wondered if any of you know if and how Peter Higgs has heard the news and what his reaction was.
I have no idea. I did hear a rumor that he was hiking in the Highlands.
I think that's a no.
Yeah, Clive Cookson from the FT. I'd like to invite you to do something that I still don't think has been done, which is to explain in ultra simple terms Higgs field and Higgs boson. I mean, there's the famous Thatcher at a cocktail party explanation, which I'm fed up with reproducing, and I haven't heard anything better.
Tom actually wrote something. I've got the pencil, Tom.
I don't even remember that. That was illustrating the point about spontaneous symmetry breaking. Now, if you try and stand a pencil up, then it's completely symmetrical. But as soon as you take your finger away, it's going to fall in some direction or another, and that's spontaneous symmetry breaking.
But unfortunately for our readers, the relation between spontaneous symmetry breaking and particles having mass is not going to be obvious. It's not obvious to me either.
No. Well, if you want some explanation of that, I have to go back a little bit further into the history. People had been trying to construct theories like this of both the strong and the weak interactions for some years, and the sort of model for this was quantum electrodynamics, which is a theory of electromagnetic interactions, and a very successful theory, and it is a gauge theory, which means it has a special kind of symmetry. And a lot of people, including Abdus Salam at Imperial College, very strongly believed that a theory of the other interactions would also be a gauge theory. But there was a problem because both the strong and the weak interactions are very short range. And that means that whatever particle transmits them, whatever particle carries them, has got to be massive. Now, the idea, or one of the ideas, was to try to create a unified theory of weak and electromagnetic interactions. And that meant some sort of symmetry between the two. In particular, symmetry between the particles that carry these interactions, the photon and the W particles, which are the carriers of the weak interaction. But the large mass of the W particles was a puzzle. There was no explanation for it, and it's breaking the symmetry between the W particles and the photon. That is the symmetry that had to be broken. And in the end, it was discovered that by adding another field, of which the Higgs is the quantum, that could be done. So it was really to give masses to the W particles. That was the aim. I don't know if that's become too technical, but
Richard Feynman once asked that same question, said, if it was worth a Nobel Prize, he can't explain it that simply. So.
Just keeping questions to journalists, Chris, if that's right. Having said that, are there any further follow-ups?
Does anyone in the room have a suggestion for a simple explanation of the Higgs mechanism, since Clive's going to need it? Any that work well in public lectures? Or?
I think the one with the crowded room is very good.
Why don't you suggest one, Clive? And they can tell
It's
if
quite
it's
visionary.
right.
We've got a physics special coming up, FT Magazine, Saturday week. Look out for that.
I think there's no doubt that the Margaret Thatcher explanation is pretty effective, actually. I mean, no explanation is going to be perfect. But
If you could run over it, that would be really helpful.
well, you have a lot of people milling about in a room, journalists probably, and Margaret Thatcher walks into the room, and the result is a sort of crowd around her, and this has the effect of adding mass, in effect, to Margaret Thatcher as she's walking through. I mean, she comes out the other side with just as much energy as she went in, but on the way she has some mass. Now, with the Higgs field, of course, this fills the whole universe. So we have to have a whole universe full of journalists.
That's a good one.
A little variation of this is that you can update it with a celebrity like Simon Cowell or something like that. Simon Cowell walks through the room, everyone will crowd around them and they'll find
Is that true?
propagate through. Whereas if a non-famous person, a non-celebrity goes through the room, they will stream through the room and the Higgs field won't interact. So that gives you another dimension. So Tom mentioned one, that celebrities are picking up extra energy and mass because they're famous in that particular context. That non-celebrities will go through the crowded room and not interact, and they're like the massless particles.
So that'll be the photon, for example,
The photon,
which doesn't have mass.
Tom.
And then the Higgs boson would be a rumor that you feed into the room and then people mill around as the rumor goes by. So that's the full analogy. But
Thank you. Any more follow-ups or suggestions, Hannah?
Just another quick one to Professor Kibble. Did you have any sense when you were publishing your initial paper that it was a really momentous proposal that you were making, and also how does it feel to 50 years on to have the proof that you've discovered something important?
No, we didn't have any such feeling, really. I mean, we were solving a problem, and we were happy that we had solved the problem, but we had no idea that it would be particularly important in the long run, and nor did anybody else. These three papers that we're talking about received hardly any citations in the first 3 years. Nobody paid the slightest attention, except to tell us they were rubbish.
When did you start to believe it, Tom? When did you start to believe these ideas were real yourself?
I always believed they were real, of course.
I think I gave you some idea of the excitement, at least people like the experimentalists. I think Tom is also a very modest person. He wrote this paper in 1967, which is also a very seminal paper. It's in this paper that he really started making the connections to what the real world looks like, where the photon remains massless and and Z bosons get a high mass. And these are the ideas that then led to the electroweak unification of Salam, Weinberg, Glashow, who'd done the work earlier, that same year. And there was a problem with this particular unification. It gave infinite answers, and that work was done in 1971, I think, if I'm not mistaken, by Duft and Weltman. These guys also got Nobel Prizes. But also you have to remember at the time, quarks had not been discovered. So it wasn't clear where these kind of ideas would be applied. And so the quarks were discovered in the later part of the 60s. And then the evidence for this extra particle that was predicted by electroweak unification, which is the Z boson, a heavier version of the photon, in fact, because it's neutral. And that was led to some consequences. And that's where the prize for Salam and Weinberg and Glashow came in, because we saw the evidence. And the last experiment that I worked on, we discovered the W and Z bosons. And that point, this is 1983 now, it's at that point when the first ideas of the LHC started. The year after, there was a big meeting, because finally the missing piece looked like to be the Higgs boson. So that's when the experimentalists had to really pay attention that you've got to go look for this boson. So it evolved as such. So it's something which we do in science all the time. Things evolve, and this is actually, as Tom has actually said, it is the closing of a chapter, but not of the story. The story continues.
And
Yeah.
Tom.
I was just going to say, initially the actual Higgs boson, as opposed to the mechanism which it's involved in, was really not that important. I mean, it wasn't a key element. It only became so after 1983, when it was the last missing piece of the Standard Model jigsaw. Everything else had been found. And so there was this capstone, if you like.
I guess I would just add that I think what this shows is that even though you don't know what the outcome is eventually going to be, it's important to have ideas and to have an environment where ideas can flourish. Students and postdocs should be able to work and have freedom to explore these ideas. You never know where they're going to lead. As we've seen, it takes a long time, but it's well worth the effort. And in doing it, we build these fantastic machines, we make fantastic spin-outs, new technologies emerge, new ideas, new momentum, all driven by an idea which someone has had. Both Higgs and Kibble had these ideas many years ago and generated all of this and all the benefits that have come of it.
Yes.
Can I just ask, whenever anybody talks about the Higgs boson, the question is always, well, what's it used for? And the answer is always nothing yet. And people are usually quite good at giving some analogies of similar kind of fundamental science discoveries that have gone on to translate into unimaginable things many years down the line. And I just wondered if you might have any of those that you could reel off, because I'm struggling myself.
Well, I said the first particle was the electron. And when you look at the word electronics, in its spelling is electron. And now imagine, but before the electronics, the semiconductor electronics I'm talking about became a reality, you had to go through the phase of atomic physics and quantum physics. They had to be there as well. So not only discovery of a particle, but then also how to use it. So electronics is really a mastery of the movement of electrons in tiny circuits. And the world has changed completely by that. That's one particular example. So that's the first particle of the Standard Model. And the Higgs boson is the last one of the Standard Model as configured. Now, so that's one obvious analogy. There are many other analogies one can make of fundamental science. It's fundamental science. Sometimes I actually say that what fundamental science gives you is paradigm-changing technologies. You couldn't have had electronics without having the fundamental science underpinning it. So it's not an improvement of a technology, it's a radical change of technology. I also sometimes classify the World Wide Web in that nature, because it has really altered the way we do scholarship, we do commerce, and we do communication as such. So it's a paradigm shift. It comes from the work that we wanted to share data. We share data massively now. Now coming a bit more closer to home, let's say the CMS experiment, we've got instruments in there. When we started, they existed in a handful of quantities. These are crystals, and we use silicon avalanche ferrodiodes. There were 3 or 4 samples, and we needed 150,000 of those. So we had to first have the courage to say, well, this is something we want to do, and will give us the Higgs boson in those crystals we found the Higgs boson, by the way. And those are now used in positron emission tomography cameras because we work in a very high magnetic field. So we had a problem to solve. So when you do fundamental science, you invariably hit problems which you have to solve, which are not encountered by others. And when you solve them, they lead to applications which are beyond what the science itself needs. And that's another example. So there are many, many examples of this nature, and I can give you a few more inside the experiments as well. Superconductivity is something, we use massive use of superconductivity. That's something which might have a future in 20, 30 years' time. It's only about 100 years ago that was discovered, and the first superconducting fluid was this much, and there are about 30,000, I've now forgotten, even I forget the numbers, huge amounts of liquid helium which are produced to cool the magnets of the machine, which are, 30,000 liters an hour or something like that. So these are the sort of things which you could mention. One, which is that paradigm shifting technologies. The second is the applications of the work that we do to actually do the science we need to do. But fundamental science underpins essentially all technology.
Yeah,
and I think this is the thing which I think is a great feature of today's announcement. It recognizes this particular aspect of science.
I think that's right, and I think I would just underpin everything you say, but